Okay, I think it looks good. Okay, so hi everyone. Welcome to the first seminar this fall. So our speaker today is, as you can already see on the screen, Scott Larson, who is the new Algebra LTAP here. And he's going to speak about small resolutions of closures of K-orbits and flag varieties. So this is the first part. It's going to be the second part next week. Okay.
Thanks, Harry. Thanks everyone for the chance to talk today. So I'll be talking about work I did in my dissertation, and it's a pleasure to talk about. So I'm happy to be here. Okay, so here's the setup for today. The first part will just be talking about words in the title, and so here's some previous work that's been done. I'm going to do similar stuff for different groups. So here's where my work begins, and then I'm going to generalize it to different groups today. So that's the plan. So first, what is K? Right, we're talking about K orbits. So what is K? So start with G being a connected complex reductive algebraic group. So for me, that means a load package Springer linear algebraic groups. So that's the starting point. So we're going to let sigma be a compact real form of G. And so, for example, here, typical example, take G to be GON. And then in that case, the typical example is transpose the inverse. And the fixed points of that is the unitary group. So that's the standard example to keep in mind. We're going to fix an anti-holomorphic involution of G of order 2. So this is some real form of your complex group. And you want it to commute with the compact form, and you're going to let that be beta. So what you get is an algebraic involution of your algebraic group. Okay, so the fixed points of beta in G is what you call K. So that's the definition. Sometimes you take it to be the connected points, the connected components, something like that. But so the fixed points in G, that's what K is. The fixed points of tau is a real reductive group. And then your maximal compact group is the intersection of these K and GR. So what's the point of all of this structure here? So first of all, GR is a real reductive group. So you can read the book like Nolan Wallach's real reductive groups and get into that book with this object. And this is sort of like the coordinate-free way of thinking about G sub R, and it's also useful for the representation theory of real reductive groups. So this is the infinite dimensional representation theory, and for example, Harish-Chandra modules are studied using this setup. So the first basic fact about these objects, if you fix a Borel subgroup of G, and you take some parabolic subgroup sandwiched between B and G here, then both the G sub R and K act with finitely many orbits on G sub R. So this is sometimes called a flake variety or partial flake variety. Okay. So that's a basic fact, and it gets used a lot in this stuff. So some examples, some simple examples here. Take your complex group to be either SL2 or PSL2, and consider linear fractional transformations. So here's an element of SL2 or PSL2, and it's acting on the chart of the projective line. Or just by matrix multiplication, and this is the same formula that you're used to for linear fractional transformations. So then let B be the stabilizer of a base point in the flake variety. This will be a Borel subgroup. And here's 3 basic examples of K orbits. If you've seen K orbits before, these examples are coming from root types of from the different root types. So the K orbits are kind of built out of these in general. So the first example that can happen is your involution is just the identity. So then kx transitively, k equals g, and x transitively on the like variety. Another basic example is if you take transpose g inverse as the involution, you get k is SO2C, and orbits on the plate variety, there's 3 of them. So these points here is fixes plus I, and a different orbit fixes minus I. And then the third orbit is everything else. And then the third thing that can happen, if you look at the same involution defined in, so this is in the complex group PSL2C, you get PSL2R. This is Atlas notation for the fixed points, and the real reductive group you get is disconnected. So that's a little exercise, and so there's just 2 orbits in this case. So the thing to take away from this example is that k orbits can be disconnected. Weird things can happen.
Okay. So in SL2R, the k is smaller than PSL2. Is only here k over 2.
Yeah, that's right. So it's an exercise to check what the fixed points here are, and you get some matrix that has no business being in PSL2R, but it's something like this. I remember right. So you get some disconnected thing. Yeah, so you think of k as being bigger. Oh yeah, yeah. So Bill asked the question. So it's a little bit funny that the k in SL2R is smaller than the k and looks smaller than the k in PSL2R. And so so the quotients there look a little bit funny. Good question. That's right, the blue and yellow are different. Yeah, so there's 3 orbits here and there's 2 orbits here. Okay, so resolutions of singularities come up. So Y and Z are complex algebraic varieties. So what is a resolution? It's an algebraic morphism, called C, and it has to be proper, birational, and smooth. So that's one standard definition of a resolution of singularities. And often if you look in some algebraic geometry books, they'll define it to be an isomorphism over the smooth locus. And that's an important thing to have sometimes, and we'll call that a strict resolution. So a couple of facts that come up in representation theory that resolutions help you with is that the variety Y is normal if and only if the push forward of the structure sheaf agrees with the structure sheaf. And then derived categories also come up in this kind of a thing. So sometimes you'll talk about rational singularities also. So for example, Schubert varieties have these properties and it is a pretty pleasing resolution. Okay, so Schubert varieties are important from my point of view here. So let's talk about them. So W is the Weyl group, and for each element of the Weyl group, I'm going to let just G sub W. So I'm thinking about this as some closed irreducible subvariety of G defined by W, and it's just the B cross B orbit closure in G. So just some notation here, the W dot is just some representative of the Weyl group element in G. Okay. So what does this give you? So given two Weyl group elements, you can define the Kazhdan-Lusztig polynomial. And so the geometry of Schubert varieties can lead to computations of the Kazhdan-Lusztig polynomial. So here's a formula for the polynomials. So one thing that comes up in this formula is the intersection cohomology. So you look at the Schubert variety. So take GW mod B in the Flag variety. Look at the intersection cohomology complex, and if you know that and everything about that, then you can get Kazhdan-Lusztig polynomial. And so those things are useful for computing Jordan-Holder series in Burma modules. So it's important for representation theory. So let's see, some notation here. If you start with a subset of simple reflections and the corresponding parabolic subgroup, so I'm going to say I is the simple reflections and P sub I is the corresponding parabolic subgroup. And so the more reflections in here, the bigger the parabolic subgroup, according to this setup. So the basic thing, if you start with a reduced word in the value group, then look at the corresponding parabolic subgroups, quotient out by an action of a product of these, and then you get a resolution of the corresponding Schubert variety. So this is sometimes called the Diemeiser-Hansen resolution, sometimes the Bott-Samuelson resolution, sometimes Bott-Samuelson, Diemeiser-Hansen resolution. So what this is like an iterated product of fiber bundle of CP1. So kind of just by analogy, I like to think of it as like configuration of magnetic balls, just kind of in different positions. Okay. And using this resolution, you can prove that all Schubert varieties are normal and have rational singularities. But one sort of fault, sort of something not as good about these resolutions is that they're rarely strict. So the fibers are typically really large. So small resolutions. So here's a technical condition for small. And intuitively, what I mean, what I think about all the time is that there's just relatively few large dimensional fibers. So if you're looking for large dimensional fibers, there's not many. And if you're looking for even larger, then there's even fewer. So there's not many large fibers. If you're taking a resolution of a normal variety, then a small resolution is always strict. So you have an isomorphism over the scoop of it. Another thing that a small resolution gives you is a handle on the intersection cohomology. So you push forward the constant sheaf and you get intersection cohomology on Y. So this would allow you to compute really explicitly Kazhdan-Lusztig polynomials if you have a small resolution of a Schubert variety. And explicitly, what you'd have to do here is calculate singular cohomology of the fibers. So something that Gelfand and McPherson did is looked at similar resolutions from Diemeiser-Hansen, but they generalized it a little bit. So now the parabolic subgroups can be any parabolic subgroup. So by analogy, I like to think about this as an iterated fiber bundle of more general flight varieties. It's, something like that, just by analogy. And another thing to keep in mind is that we're quotienting by more general parabolic subgroups. And you always want to take the quotient to be as big of a group as possible in this. The bigger the parabolic subgroup, the smaller the dimensions of the fibers. And that's the goal. Is R right here? That's a very good question. Bill asked, should this be the same? And the only condition you need is that it's at most as big as that. So it is useful to allow smaller parabolic subgroups. So I think what you're getting at is that this is not always a resolution, and that's true. So this will be a resolution exactly when the dimension of the image is the same as the dimension of the domain, and that just doesn't always happen, even if you allow this R equal to P.
UGI is not they all have or
No.
don't
Yeah, they can be really anything, and then just at the end you want to check that you get a generically finite prism that's birational, and then it'll be a resolution. Okay, so I'll go through an example in the next slide. I think it'll help things. But let me just mention that what Zelevinsky did is he took Gelfand-McPherson's construction and described in a very nice way using combinatorics of things like file groups. He described what parabolic subgroups you have to take in order to have a small resolution of every Schubert variety in grassmannian flake varieties. So let me just do a quick example here. I hope it's somewhat quick. So G is GL4, X is the flake variety. So this is the set of all complete flakes. You have a subspace of each dimension trapped between 0 and C4. So this projects, the flake variety projects pi down to flake variety, partial flake varieties corresponding to bigger parallelic subgroups. So let me call it something like xi, and so that's just G mod pi. So for example, if you take I equal to everything except for 2, S is 1, 2, 3, the semi-simple rank of G is 3 here. Then xi here is the grassmannian flake variety of 2 planes in C4. So a subvariety of xi is this, what I call y here. This is sort of the first singular Schubert variety that comes up in many examples. You intersect the 2 plane in C4 with C2. Sorry, I didn't say what C2 is. So I always take C dot to correspond to corresponds to the Borel subgroup. So here's CK is the span of the first K basis vectors, standard basis vectors. So intersect C2 with E, and you have to get dimension at least 1. Okay, so here's what Zelevinsky said. In fact, this is in Gelfand-McPherson's paper too. So, so here's the parabolic subgroups you start with, and so let me say that the trick that Gelfand-McPherson talked about. So if you start with a quotient like this, then you can describe it isomorphically as starting with a base point, and look in the product of G mod R's. Okay, and then describe the fiber product by over the G mod P's. So this is what Gelfand-McPherson said to do, and if you do this, then it's an isomorphic to the quotient of that. So so these have really nice kind of fun pictures. So here's how I think about this. So B mod B is like the base point here. So you start over a base point. And then you're looking in a product of flake varieties. So you have to figure out which subspaces to implement here. R1, R's are going to correspond to J's. I have to do this to make sure everything's right. So the largest parabolic subgroup that makes a well-defined quotient is the intersection. You can intersect the simple reflections, and intersect I1. Is 1, 3 intersect 2, 3. 1, 3, and 2, 3, that's 3. Okay, so G mod R1 is you omit the dimension 3 subspace. Sorry. And then G mod R, J3, you get the same looking like variety here. Okay, so now we're realizing Z and a product of these things, and then I have to say what the relations do. Okay, so you project to I0 is 1.3, and so in the projection, these two spaces have to be equal. I'm getting that from projecting to this flag variety. Okay. And then G mod PI1 is everything but 1. So I get that these two have to be equal. And I'm getting that from this relation right here. Okay, so often you'll see these things drawn a little bit differently and nicer. So what we get, I'm just gonna get rid of the equal signs. And there's a one. Two. Two doesn't have to be in C3. So that's how you get diagrams that look something like this. So I think that's one of the nice tricks that Galfan and McPherson said how to do. So notice that this is I guess I should have wrote C2 instead of R2. So you could say that this is the set of lines and planes where F1 is contained in C2 and E2. So, C2 and E2. So that's how you go from quotients of parabolic subgroups to subvarieties of a product of like varieties. So the resolution ends up just being a line contained in C2 and E2, and then you project to E2, and that's the resolution of the Schubert variety. Okay. Okay, so then Barbasch-Evens did the same thing for k-orbit closures for 3 different real reductive groups. So that's what we'll look at here. So similar to the case of the violet group, I'm going to let V be KGB instead of BGB. So for every KGB, V dot is an element of G, and it's the K cross B orbit representative in the group. So look at, so then G sub V, I'm saying, is this closed irreducible subvariety of the group, K cross B orbit closure. Just the same notation we had from before. So J is going to correspond to R, the J's correspond to R, and the I's correspond to P. So what they did, so if you look at the projection of flag varieties, so here R is contained in P, and so that means there's a projection from G mod R to G mod P, projection of flag varieties. And if you restrict this map to smooth k-orbit closures in the domain, then sometimes you can get a resolution of singularities that way. So that's what they use to construct resolutions. In fact, they describe it somewhat differently, but isomorphically, you can describe all the resolutions like this. So So here's the three real reductive groups that they considered. And one thing that they can say is that all of the k-orbit closures in the grassmannian flake variety are normal for these groups. So all of these have k contained in GL. And so that it's acting on the grassmannian. So all the k-orbit closures are normal there. And in this case, if the real reductive group is UTQ, then they were able to say that all of the k-orbit closures have small resolutions in that case. So they found a family of small resolutions for these k-orbit closures. So just a quick example here. Here is one of the k-orbit closures for U44. So instead of just intersecting intersecting the base point in C4, you also have to intersect it with like the opposite base point. So here the notation is stabilizer in G of C minus is the opposite for L. So that's with respect to the standard torus. So for example, C minus K is the span of the last K standard basis elements. So that's all I have to say. Okay, so this is a singular k-orbit closure, and they described, Barbasch and Evans described how to find a small resolution of this. So here's what you do: you take a plane in C4 and E4, a line in C minus 4 and E4, and that turns out to be a resolution. So the reason, I mean, this doesn't look so smooth at first sight, but the reason it's smooth is because you can describe it actually as a smooth k-orbit closure in a flake variety. So, so what you do here, let's see, go to C8. And you look at the grassmannian of three planes here. The closed k-orbits are where F3 is its intersection with C4 and C minus 4. So one of the closed k-orbits, this is kind of how I draw it here. It's intersecting C4 in dimension 2, and it's intersecting C minus 4 in dimension 1. So that's a closed k-orbit in the grassmannian. And then you pull it back to include four spaces, four planes. So if you pull it back to a larger flake variety, you get that. And so that's why it's a smooth space. It's a fiber bundle over a smooth k-orbit with smooth fiber. Okay, so what I did in my dissertation was the same thing for a different group. And what I found is that this is a more complicated situation, to summarize it. Okay, so here I'm starting with the complex group to be sp2nc, and I like taking the symplectic form corresponding to S minus S, and here S is that matrix. So I think if you've seen this symplectic geometry before, often you take an I and a minus I. So this is just sort of lining things up better. So you can take, for example, the Borel to be upper triangular matrices. Okay. So K is black diagonals in the symplectic group. So it looks like this. All of these matrices in the symplectic group, and it's isomorphic to GLNC. So we're looking at orbits of GLNC on the symplectic flake varieties. So if you want to describe the geometry of these things, it's usually easiest to start with maximal parabolic subgroups. The bigger the parabolic subgroup, the smaller the flake variety. So let's see, the flake variety in this case, the symplectic group is all k-dimensional omega isotropic subspaces of C2M. So something we need to look at here is a projection. So lambda plus is going to go from C to n to C plus n, lambda minus to C minus n, corresponding to this direct sum. And I'm going to define 3 integers to classify the k-orbits. So to get the first 2 integers, A and B, is the same integers that Barbasch and Evens use in type UQ. That's the intersection of a thing with Cn, that's A. The intersection of E with C minus n, that's B. And then to get the third integer here, I need to define a symmetric bilinear form on the subspace, the isotropic subspace E. And so it's sort of an exercise, I guess, to check that this is actually a symmetric form. And so I can talk about the radical, and I'm going to say C is the dimension of the radical minus A minus B. So it's kind of, it's a fact that these subspaces are always contained in the radical, and then sometimes you get extra dimension. And C is the extra dimension. Okay, so then the fact is that KGP, the k-orbits on display variety, correspond to these 3 integers as long as these conditions are satisfied. And it's a little bit better than that. Using these combinatorics, you can say what the closure relations are. So if you think about when is one closure contained in the other, so A prime has to be at least A, B prime has to be at least B, and then the sum has to be. At least it's the other two.
Can I ask a question?
Yeah.
Where did little k come from?
Little k, that's a good question. That's the parabolic subgroup. This is like piece of k hat. So little k is the defining the Blake variety.
You're allowing any maximal parabolic right now?
That's right. Yeah, any of them.
Okay, thanks.
Yep. Okay, so now that we know what the orbits are, we can start looking at their geometry. And so I was able to construct a resolution for all of these k-orbit closures in any of the maximal parabolic Blake varieties. And it's a uniform construction, so it looks the same, just depending on the parameters we have. So if we start with any k-orbit in the Blake variety, so we're going to set the space in a product of isotropic grassmannians. So here I just use the bullet because the dimension of the spaces change. And so all we have to do is, so a line here means that this space FA plus B plus 2C is contained in FK plus C, and EK is contained in FK plus C. And I also want to force the dimension. So sometimes I write this as like that. This intersects Cn in dimension A plus C, and it intersects C minus N in dimension B plus C. Okay, so if you start with that as the space and project to EK like this is just projection, then it's a resolution of the k-orbit closure. So maybe one thing I'll mention is that this is a little bit more complicated than just projection of Blake varieties. You have to start with a smooth k-orbit closure, and then look at. So it looks kind of like this. You start with some smooth k-orbit closure, and then there's like a Blake variety fiber. So it's something like this. And I'll talk a little bit more about this way of thinking later. That's projecting to. So that's kind of what this looks like. In other words, you can't just take a smooth k-orbit closure. You have to sort of do what Duffon and McPherson did for Schubert varieties, where they started at a base point and looking at fiber bundles over a single point. And now I'm thinking about starting with a smooth Kerr closure and looking at fiber bundles over the smooth Kerr closure instead of just a base point. So that's why it's smooth. Okay, so now that we have a resolution, we can compute things like the dimensions of the K-orbits. Since it's birational, the dimensions on both sides are the same. And the base is just some iterated, or it's just a fiber bundle, so you can calculate dimensions easily using that. So here's a formula. I don't recommend writing this down or anything, but it's a formula for the codimension of one orbit closure in another. So that's important if you want to find out when a resolution is small. Codimension comes up. So let's look at one example. If K is at most n over 2 and C equals 0, then the K-orbit closure is you don't have to worry about the radical. So it's just the intersection of E with Cn and intersection of E with C minus n in the correct dimensions. So in this case, the fiber you can describe as a product of grassmannians. So that has a nice dimension formula. So to show that this is a small resolution, you have to compare this expression to this expression, and I just want to kind of point out that this like a prime minus a shows up, and some things cancel nicely. There's a nice grouping of terms. Okay, so there's a family of small resolutions. So after looking at a lot of resolutions, I eventually realized how to generalize this to any case. So if you start with some KGB element, so I'm going to think about this as a smooth K-orbit closure, but maybe I'll worry about that later. So in other words, it's useful more generally than that. So I'm going to start also with M Weyl group elements. Yeah, now I'm in any KGB, and I guess for this I just want to assume that K is connected. But all the statements make sense. They're just a little bit harder to say for any case. So yeah, this is for any K. Okay, so define this product here with the quotient of parabolic subgroups, and all I want to do here is assume that the quotient is well defined. So so this R sub 1 has to act by multiplication on the right of GB naught and on the left of GW1. So this is a standard parabolic subgroup because these things are always B stable. So B works, and then you just want to take the largest possible to get the smallest fiber dimension. And it's possible to say combinatorially what the largest parabolic subgroup can be. So to do that, I need to think about a monoid action. So here I'm going to say U is V star W if GU mod V is the image of just two peaks like this, if M equals 1. So then let's see, if V equals W, then this defines a monoid on the Weyl group, monoid structure. And in general, we get a monoid action. In general, the monoid acts. So another way of thinking about GU here is in the complex group. It's what is the image of multiplication here? It's just that. So this is taking place in the group. So now that I have a monoid action, there's a common invariant here, tau of V is the set of simple reflections such that E star S is V. Okay. So this also applies to file group elements. If you're looking at, so David-Vogan originally defined this in his papers about characters. And so if you look in that paper, I should probably call this a weak tau invariant to sort of agree with what he's saying, but if he considers local systems too, I typically leave the W off. But okay, so so with this definition, I'm going to tell you what R1 is. So R1 corresponds to the simple reflections J1. That's tau of V intersect tau of W1 inverse. So the similar formula holds for all of the R's. So if you take that to be your parabolic subgroup there, that's the biggest it can be, and so the smallest fiber dimensions. Okay, so one sort of easy formula from all of this is describing exactly when this this morphism mu from Z to the flag variety, when is it generically finite onto its image? I mean, if you want a resolution, that's one property it has to satisfy. And more generally, if you're considering local systems on the K orbits, then this is an important property for studying local systems. So it's easy to say when it's generically finite. And I used a computer for U22 to compute all pairs like this, where it's generically finite, and about half of them are generically finite, and half of them aren't. And so that's just what happens. So maybe I'll just say that this formula comes from thinking about this as an iterative fiber bundle, right? So I guess in analogy, this is like you're like starting with some K orbit, and then you're looking at weird Schubert varieties over it. So it's just more general than before. Yeah, I guess I always use a computer for this formula. It's sort of too long to really look at in many examples. Okay, so using this this general construction of resolutions, I went back to the symplectic group, and I was able to find many families of small resolutions. So all of these use different parabolic subgroups in that construction. So I mean, some of these are kind of interesting. So I know that this family right here is actually bijective. So it's a small resolution, but I don't know that that the K orbit is actually normal, and so who knows if it's smooth or not. If it was normal, then this would actually be an isomorphism, and not just kind of a trivial small resolution. So then maybe a couple of comments about these resolutions. Are there yeah, that's a good question. They'll ask if there are examples of K-orbit closures that are known to be non-normal, and the answer is yes. Barbasch-Evens and SP8R found an example of a K-orbit closure that's not normal, and the way they did that was they looked at resolutions of an example of a certain type of what I was talking about before. So they would be this. They would start with what they call the distinguished K-orbit closure, and look at simple parabolic subgroups. So like a fiber bundle of CP1s over the K-orbit closure, and something like this. So they looked at resolutions of this type, and they found a birational map onto a k-orbit closure with disconnected fibers. So it's not normal in that case. I mean, I guess one kind of interesting thing is the only example of k-orbit closures I know that are non-normal always have a disconnected fiber like this. So like for Schubert varieties, that's how you prove they're all normal. And for some k-orbit closures, you can prove they're normal using this. And then on the other hand, you can also say some are not normal using this.
Yeah, because you wonder what goes wrong. Well, just so happens that I have I hate that.
Yeah. I mean, so it just contradicts our seasoning theorem. So that's not somewhere. And yes, I mean, they do look at it. That's not.
Well, you kind of get into a fight. I guess in the absurd technology, this resolution now is in so I'm going to use to see what circumstances.
Yes, so I know that the Barbasch-Evens say some things about if your closure is normal, certain K types appear in the sections. So it's like I think of it as like missing K types kind of a thing, but I haven't thought too much about it. Okay, so do I have until 4:50 or 5? Okay, so I'll just conclude with a couple comments about what some nice things for all of these resolutions that they have in common. So what I was looking at is not all Schubert varieties in the quotient, but only when there were parabolic subgroups like this. And so I was looking for all of these in up to SP12 in the maximum parabolic varieties. And so I wrote down all of the small resolutions of that form for up to SP12. And so then all of them generalized, and then I was able to describe the families and then recover all of the examples. So that was kind of a neat thing that happened. Yeah, that's right. That's a good question. Bill asked if the PI1 is an example of the GV, and the answer is yes. So WI equals W. Maybe I'll just say I sub I, and that's the maximum in the valid group generated by simple reflections. Then in that case, GWI is P I sub I. Yeah. I think two interesting things happened. One is that all small resolutions, all of the families, when they were small, you can describe them, they sort of like degenerated to something like what Barbasch-Evens looked at. So I thought that was an interesting thing. Yeah, so when they were small, they were just a projection of diagrams. And then just like one thing, that's right. Yeah. So even when the resolution that works for all of the k orbits, when that's small, it degenerates to just the projection. So I thought that was interesting. I don't know what it means, but the second thing that's important for some things I'll say next time is that all fibers of small resolutions from the previous slide are smooth. And so that was unexpected also. There's something like products of grassmannians. So let me end there. Yeah, are there any questions? From anyone at home? I think so. Oh, they're clapping. Thank you. How do I stop this and make sure it's